This is Professor Stephen Sekula from Southern Methodist University, and this is part two of a two-part lecture entitled Electric Fields and Energy. Now, in the last lecture, we discussed changes in potential energy and how those relate to the path that you take through an electric field if you are, say, an electric charge. So we defined the change in potential energy between 2 points, A and B, as delta U, AB, and that's equal to the potential energy at B minus the potential energy at A. And because of the relationship between mechanical work and changes in potential energy, for instance, work done by a field on a charge, this is equal to the negative of the work done by, say, the electric force in moving a charge from point A to point B, and from the definition of work, we arrive at the electric force, which is QE, dotted with little pieces of the path, and that whole thing is integrated from A to B. So this is just from the definition of work, substituting the electric force in, and this is the definition of changes in potential energy. And again, we're talking about, for instance, if we think a positive charge moving along a path from A to B, so here we have Q greater than 0 and some electric field pointing down from A to B, then we have a situation where UA is higher than UB. The potential of UA is higher. The electric field, when it does work on the charge, will move it to a lower potential energy location. And so UA must be greater than UB, which means that UB minus UA is less than 0. And in order to get a relationship between that and the positive work done by the force field, you see we have to put a minus sign in front of the work done from A to B. Now, this definition is great. It's very helpful. It allows us to relate changes in location in an electric field to the fundamental concept of changes in potential energy, that is, the energy of configuration, the energy you store in the electric field by doing work against it in the first place and then letting the field then do work on the object. But what we really need is we really need something that's kind of independent of this little beast here, Q. If we write this out in a simplified form without all this intermediate stuff, we have that the change in potential energy from A to B is equal to this quantity. But we've got this pesky charge floating around. We don't know what that charge is. And so it's very convenient to divide both sides by Q and define a new quantity, the electric potential difference between 2 points, which is defined as the change in the potential energy between those 2 points per unit charge, and that's going to be equal to negative the integral from A to B of E vector dot dr. This is a very useful quantity. Let's stop for a moment and think about units here. First of all, we have work. Work is energy. It's mechanical energy, and it has units of joules. Those are the MKS units of energy. J, which is equal to kilogram meter squared per second squared. Well, changes in potential energy are just changes in energy, so they also have units of joules. So the units of delta UAB are also joules, and the units of charge are coulombs. So the units of electric potential difference, the energy per unit charge, is just joules per coulomb. And that gets its own name, the volt, whose symbol is just a capital V, not to be confused with volume. So be very careful if we're ever talking about both volume and electric potential difference. Now, the volt is a very common unit in our lives. For instance, when we talk about batteries, we talk about voltages. Let's say in a battery, your typical car battery has a voltage of 12 volts. Now, when we say that a battery has 12 volts, what we're really saying is that for every coulomb of charge that moves from one terminal of the battery to the other terminal of the battery does 12 joules of work on that coulomb. Okay, so let's put this in sort of concrete terms. We have a battery that's 12 volts. It has a positive terminal and a negative terminal. The positive terminal, you can think of that as emitting positive charge, and the negative terminal you can think of as emitting negative charge. And if you have a 12 volt battery, it means that for every 1 coulomb of charge that moves, say, from point A to point B, the positive terminal to the negative terminal, through a circuit, for instance, for every 1 coulomb of charge, the battery does 12 joules of work to make that happen. That's what this means. Okay? That's why voltage, this electric potential difference, is so convenient to think about. Now, there are many other common voltages that occur in nature. Batteries are human-made concepts, but there are some very natural concepts that also have voltages. So, for instance, the voltage, let's say, between the human arm and the leg due to the heart. The heart is an electrical appliance. It uses electricity and movement of electricity in order to generate the pumping action. And as a result, this creates a voltage, an electric potential difference between your arm and your leg. And that voltage is 1.0 times 10 to the minus 3 volts, or 1 millivolt. Okay, so it's a tiny electric potential difference, but such a critical one to life. Across biological cell membranes, so cell membranes, it is in fact the electric potential difference across a cell membrane that allows charge to move in and out of the cell, and it's this process of moving ions around through the cell membrane that then leads to larger electrical properties of biological material. And the voltage responsible there is typically about 80 millivolts, so much larger than the tiny voltage between your arm and your leg due to your heart's electrical activity. Flashlight batteries, 1.5 volts, car batteries, 12 volts, electrical outlets, your outlets on the wall. Those are, depending on what country you're in, 120 to 240 volts. Okay, so again, that means that for every coulomb of charge that moves from one plug terminal to the other plug terminal on an electrical outlet, say through your blender, that wall outlet, the power plant at the other end, is doing 120 joules of work in order to move 1 coulomb from one terminal to the other. That's the definition of electric potential difference. Delta VAB equals delta UAB over Q, which is equal to negative WAB, the work per unit charge. Okay, so let's keep all of those definitions in mind as we go forward here. Now, a very special case that we can treat very easily is the uniform electric field. We've done this one many times now. The strength of the electric field is not a function of space. It is simply equal to a number, a positive number E, times a direction. Let's call it I hat. And let's say you have a charge Q that is in this electric field, and the electric field is going to do work on the charge and move it from a region of high potential to a region of low potential. Now, what direction that translates into depends on whether the sign of the charge is positive or negative, as we discussed in the last part of this lecture. But let's write down our relationship between the electric potential difference and the electric field, which is E vector dot dr vector. So again, let's imagine that our electric charge starts out at a point A and follows some path to a point B. Okay? Now, the electric field is not a function of position. We can write it in here, in fact. Delta VAB is equal to negative the integral from A to B of E I hat dot dr vector. Well, I hat points to the right, and the little pieces of our path, the little dr's that add up to make the total path, they also are all parallel to I hat, point in the same direction, and in fact, the unit vectors themselves are equivalent to I hat. So we could write dr vector as equal to its magnitude, the magnitude of that little length dr, I hat, because I hat is the unit vector for the dr vector, at least according to the picture that I've drawn here. So we can substitute that in. Delta VAB is equal to negative the integral from a to b of E I hat dot dr I hat. And we have a unit vector times itself. Unit vectors have length 1. The product of a vector with itself is just going to give you the magnitude of the vector squared, and since the length of this vector is 1, the magnitude squared is also 1. So this greatly simplifies, and we just have E dr. Now, as we've been saying time and time again, the electric field strength is not a function of where you are in the field. It's a constant, and so it is not going to participate in this integration. It comes out of the integral. And we have the integral from a to b of all the little pieces of the path dr. This is a very simple integral. It's just equal to negative e rb minus RA. And this is just the length of the path. Okay? So in the special case of a uniform field, the potential difference between 2 points A and B is just equal to the difference in positions of the 2 points times the electric field. E delta R with a minus sign in front of it. Now let's think about what this means for two cases, Q greater than 0 and Q less than 0. For Q greater than 0, delta VAB will be equal to negative E delta R. Delta R is a positive number in the picture that I've drawn. E is a positive number, so overall this will be a negative electric potential difference. Does that make sense? Well, the positive charge is going to move in a direction that takes it from a region of high potential energy to a region of low potential energy. You would expect, therefore, the difference in potential energies of the 2 points to be negative. This is then equal to the change in potential energy per unit charge. And so if we want to find what the change in potential energy is, we just can solve. Delta UAB is equal to negative Q E delta R. And we see that the change in potential energy is negative, which is what you'd expect for a positive charge moving to the right in an electric field. Now, what if instead the work that's being done is moving a negative charge from the left to the right in the same field? Whereas the positive charge going to the right is a bit like a ball rolling downhill in a gravitational field. If a negative charge is moving to the right in an electric field, it's like somebody pushing a ball uphill. It's going against the direction that the electric force wants to move the charge. So while in this case, delta VAB still has the same properties. The path is positive, the electric field is positive, so the overall electric potential difference is negative. In this case, however, delta UAB is divided by a negative charge. And so what we find is that for a negative charge moving against the grain of an electric field, that is, from a region of low potential to a region of high potential for a negative charge, you get the answer you'd expect, that the change in potential energy is not negative, it's not decreasing, it's positive, it's getting bigger. You have to do work against an electric field to make this happen. And this is what the change in potential energy is going to be equal to. Now, it's important to stress again and again and again that this is only a quantity which is relevant between 2 points. And not only that, it's independent of the path. We could have set up a simple example back here where the path was not a straight line from left to right from A to B, but rather a squiggly line. But because of the nature of the dot product, all the little squiggles perpendicular to the electric field aren't going to contribute, and all that's going to matter are the little pieces along the electric field, which have the same total length as the straight path I've drawn here. And so in the end, you get the same answer, but you do it with a lot less work if you just consider the straight path. It's very common to shorten this to just be V rather than delta VAB. It is implied that we are measuring the electric potential difference at some other point relative to point A, and you can simplify the notation simply by writing an electric potential difference as V and calling it a voltage. Okay, so a voltage will always be an electric potential difference, especially when we start talking about electric circuits. It describes how work will be done on charges in the system. If you know the voltage, you know the work that's going to be done moving a charge from any point A to a point B, regardless of the path. And you can simplify your notation rather than having to write delta VAB all the time. It's just writing V, where in an electric sense, V is voltage or electric potential difference. It's not volume. Okay, so don't confuse those two things. The last thing I want to talk about today is the electron-Volt. In molecular, atomic, and nuclear systems, which are very tiny systems, okay, so for instance, you may recall that the mass of the electron has a value of 10 to the minus 9.11 times 10 to the minus 31 kilograms. This is an exceptionally tiny number. And you can imagine that when we talk about energies of electrons in atomic systems or in molecular systems, we're talking about minuscule amounts of joules, extremely tiny, tiny, tiny amounts of joules. Rather than carrying all of these tiny numbers around with big scientific notation powers on them, it's convenient to define an energy that's more appropriate to very small things like atomic or subatomic systems. And so we define the electron-Volt. The electron-Volt is the energy gained by a particle that carries 1 unit of elementary charge, okay, for instance, an electron. It's the energy gained by that particle when it moves through a potential difference of 1 volt. So let us imagine that I have 2 points, A and B. I have a charge, Q, which is equal to the elementary charge, 1.6 times 10 to the minus 19th coulombs, and it moves between point A and B. The energy that is gained by the charge when it moves through an electric potential difference, delta VAB, which is just V, which is 1 volt, that is going to be equal to 1 electron-Volt. Here's how you can see it. The energy gained is going to be equal to delta U, and that is going to be equal to Q times delta V. So there's our electric potential difference. It's 1 volt. There's our charge. That's 1.6 times 10 to the minus 19 coulombs. And this is the change in energy. This has units of joules. So we can say that 1 electron-Volt is equal to 1.6 times 10 to the minus 19 volts times coulombs, which is equal to 1.6 times 10 to the minus 19 joules. That's the definition of the electron-Volt. 1 electron-Volt is equal to 1.6 times 10 to the minus 19 joules. And typical energies in atomic systems are of the order of the electron-Volt. For instance, the energy required to remove an electron from the lowest orbit of a hydrogen atom is 13.6 electron-volts. So you see that this is a very convenient number for discussing energies at the scale of atoms and certainly at the subatomic scale. That's it for these lectures. We will pick this up next week and talk about how to calculate electric potential differences for more complicated things, such as in the point charge. And then we will move on to the discussion of how to store energy in an electric field and make that energy work for you in the form of a capacitor.